We will discuss the circuit constraint, or a constraint which is useful to enforce an Hamiltonian circuit, which means that you need to visit every city exactly in a graph. Okay, and to model this problem, the Hamiltonian circuit problem, which is a frequent subproblem that you may see in many different contexts, like vehicle routing problems or the TSP, we will use what we call the circuit successor model, the successor model. For the successor model, we will encode the next visit that you need to visit at each index. So let me show this on an example here. It means that these are all the indices of the city, and what it means here, these are this is what we use to encode a Hamiltonian circuit, which is a permutation of all the cities. We just say that after visiting the city at index 0, we will visit the one at index 2. Okay, like this. So after the one at 0, we will visit the one at index 2, and then you may already guess what is the one that will be visited after 2. For that, you just go here at the index 2, and the next one will be the one at index 1. Okay, so we will move to index 1 like this. Then to visit the successor of 1, we just read this number, which is 4. So from 1 we will go to 4 here, like this. Okay, then after 4 we will visit 3. This is given here, like this. After 3, after 3 we will move to 5. Okay, so we will jump here, and after 5 we move back to 0, and we've got a circuit. Okay, what you can already see is that in order a Hamiltonian circuit, we must have a permutation here, which means that all the numbers at least must be different. Okay, so we have at least an all different constraint that is enforced here. But this is not enough, right? This is not enough to enforce that you have a proper Hamiltonian circuit. Okay, what you also need is subtour elimination. So you cannot have a situation in which you will visit only a subset of the cities. Okay, and this is also possible. Let's see one example like this one. Okay, in this example, which is a counter example, you've got a permutation which is fine. Okay, the permutation is fine, but you've got two subcircuits here. You see, after having visited the city 0, 1, 2, 3, the city 3, you will jump to city 5, which is given here, and after the one visiting the one position 5, you move back here. Okay. And so you see what you have is that you have an inner loop, and this is of course forbidden to be a Hamiltonian circuit, because you can only have one single circuit to visit all the cities. Okay, so we need to remove the possibility of having that, and this is why this constraint is a little bit challenging to filter. Okay, so you've got two subcircuits here. One which is represented in purple, and the other one is the yellow one. Let's model the traveling salesman problem with this constraint. You will see that we can do that very easily. So if you remember, the traveling salesman problem is the one in which you want to minimize the total length of the Hamiltonian circuit among a set of cities. To do that, in input, we need some data, of course. We need the distance metric. So we need a metric that will encode the distance between every pair of cities, for instance, between this one and this one. Okay? And so what we do here is that we read this distance metric, which is n by n, so a square matrix n by n, with all the distances between every pair of cities. Okay? It can be asymmetric or it can be symmetric. Okay? It depends if it's an asymmetric traveling salesman problem or a symmetric traveling salesman problem. Then we create a bunch of variables to model the successor model. And we have the successor that is visited next after each city. And so this is why the domain is also n here. Okay, we've got an array of n variables, and every variable can visit all the other n next city, possibly, of course. We don't know which one will be selected, but initially this is the domain that we give. Then we've got the objective function here. Okay, we post the circuit constraint. The Hamiltonian circuit constraint is posted. And then we have here the collection of all the distances to the next. We've got the distances to all the next cities that are visited. And so for every city of the tour, we compute the distance to the next city, which is given here. Okay, so the distance the distance from the city I to its successor is given here with this element constraint. Okay. Once we have that, we can compute the sum with the sum constraint that we have already seen last week. We want to minimize the total distance here, and then we have the DFS, and we use a first failed heuristic, for instance, to collect and discover the best subcircuit. That's it.